Hello guys, welcome again to the channel. My name is Amos from Acoustics. Today's video is a continuation of the previous video that I did, and it's all about building acoustic panel, professional acoustic panel. The only difference is that today we are building broadband absorber. So I'm here to show you how to build professional effective broadband absorber, or otherwise known as bass trap. Before we proceed, let's first clarify at what point are we talking about bass frequencies. What is the crossover point? Because as you can see the chart here, we have the lowest of the low, which is the infrasound. Infrasound frequency is below 20 hertz. 20 hertz, we can't hear anything below 20 hertz. Then from 20 hertz going now all the way to 60 hertz, around that area, we have sub-bass. Now we're talking about large subwoofers, or generally subwoofers. They produce 20 to 60 hertz in most cases. That is sub-bass region. And then from 60 hertz all the way now to around 250 hertz, then that is why we have general bass that we hear in bass guitars and a lot of bass instruments. Now the question is, why 250? 250 actually is what we call Schroeder frequency. Schroeder was a German engineer, acoustical engineer, who calculated and came up with that concept. So it's the frequency in most small rooms. There's a formula for calculating Schroeder frequency. I'm going to show it right here in the screen. You can calculate Schroeder frequency on any room, but in most small rooms is around 250 hertz. That is the crossover point. It's the point at which now the sound transitions from being directional, like directional in this manner, to being something like this, wave-like, ocean wave-like kind of energy, omnidirectional, powerful and large. Now 250 hertz is the crossover point, technically referred to as Schroeder frequency. Now first, to build acoustic panels that will absorb these frequencies, there are certain parameters that we need to really look into very keenly, because look at these two panels here. I'm going to work on this acoustic modeling website here. It's going to show us two panels. We have these parameters. Parameter number one is the gas flow resistivity, that is porosity vis-a-vis density. And then parameter 2, we have things like depth or thickness. Then parameter 3, we have air gap. So the concept of air gap, we're going to look into it after building the panel, so we see how it impacts the performance of the panel. Now let's take these two panels, and one we're going to use rock wool material, very dense, 100 kilograms per cubic meter. It has gas flow resistivity of 50,000 pascal per meter squared. In this other model, it's rails. So rails and pascal per meter, they all represent gas flow resistivity. It doesn't matter the unit at this point. So one we're going to use dense rock wool, and then this other one we are going to use glass wool. Now the only difference between these materials is density, and let me talk about gas flow resistivity or porosity in this matter. So if you look keenly at these two graphs, one that is made of rock wool is kind of not working very well below 500 hertz. Remember, the thickness of both panels is 20 centimeters thick, or 200 millimeters, or 8-inch thick. You can imagine how thick that panel is. Like this one I have behind, I'll have a couple of these 8-inch panels in this room. They are doing a great job here. So you can see the one that is made of fiberglass, fluffy material, low density, has very low gas flow resistivity. In this case, it's 8,000 pascal per meter squared, while rock wool has a flow resistivity of 50,000 pascal per meter squared. You see the performance of rock wool doesn't do very well. Actually, it's not even a bass trap. It's still not absorbing even enough of lower mids below 500 hertz. So basically, what you're saying is that the 20 centimeter rock wool panel does the same thing that 4-inch or 3-inch panel of the same would do. So it means we have wastage of material there. The performance is so low. On this other side, look at the fiberglass, the fluffy material. It performs very well towards the lower frequencies, works all the way to around 80 hertz, and you can check that in the diagram there. So these are some of the factors that we need to take into account before we build a bass trap, because they can look the same but the performance is totally different. Now let's take a look at the air gap behind the panel. Now suppose we have a space, or in this case let's push them to the corners. We like placing them at the corners because we have space there. You can play with the concept of air gap, and normally it gives us around 200 millimeters or 20 centimeters of air gap behind the panel. So let's type 200 millimeters behind each panel and see how it impacts the performance of the panel. You can see the impact it has, especially on the fluffy the fiberglass panel. it does very well. Actually, it enhances more frequency absorption toward the lower end, while on the raw cool still we don't get any serious absorption no matter what we do. So you can see how all these parameters are very, very important. So if you're going to build a thicker panel, make it very low density in terms of the core material. In this case, use glass wool. If there's a raw wool that has lower flow resistivity, then you can also incorporate that into the core of the panel. Then you get very good absorption towards the lower frequencies, which is what we want. Now the question is, at what point does thickness cease to matter? Because it reaches a point where now it doesn't matter how thick you make the panel, it will not do anything good. Now let's check at this diagram here and make these panels a bit thicker and see if they can do anything. Let's make them 30 centimeters thick. That is literally 1 foot thick, very thick. I don't know if a lot of us have this space for 1 foot per panel, because that will be eating a foot all the way around the room, which is kind of problematic for most small room. Now let's model a panel of the same thickness, 1 foot each, and see if it does anything to the frequency response. Okay guys, now after modeling these panels and making them thicker, both raw cool and the glass wool panels, you can see raw cool barely changed in terms of absorption. There's no adjustment at all in terms of low frequency absorption, but the glass wool, on the other hand, there was a slight increase in absorption toward the lower frequency. But you can see the problem is that it reaches a point where it doesn't matter how thick this thing is. We are talking about 1 foot thick of a panel. That is a very huge chunk of a panel, but still cannot absorb enough. It doesn't work very well around 60-50 hertz range. So the question is, how thick should we make these things to make them absorb? Let's talk about 50 hertz. If you want to absorb 50 hertz, we realize it would not be practical using the porous absorber. So there are technologies that engineers developed over the years that were tailor-made to absorb frequencies that low, the sub-bass area. So if you are a mixing engineer or you're a mastering engineer and you want almost no room interference in your mastering session, then I would advise you find a solution that can be able to tackle 50 hertz. So we have technologies that are tailor-made. If you don't know, some of them are things like membrane absorbers, where they use the different technology. It's not the porous absorber that we just designed. And then we have things like Helmholtz absorbers, low frequency management systems. These have been developed over the years to tackle, especially in pro studios, where you design studio from the ground. These have been incorporated into build of several studios. Literally, I've never built any of these, but I'm eager to really build one. And when I build one, I'll put them in the studio and just see how well they work. They work by targeting specific frequencies and bringing them down, like kind of shooting them down. So for this video, that's how you build a broadband panel, porous broadband panel, by taking into account the thickness and the porosity. And you can see the porosity is such a big deal in this case, and things like air gap, which you can also look into. So thank you guys for watching. Stay tuned for the next video. Like, share, and subscribe.